Good morning, everyone. So what we're going to do today, it's my intention is for it to be a fairly short class, and then we can maybe about half the time, maybe about a half an hour, and then we can move into talking about any questions you have, homework assignments, and the like. But what I want to do is I just want to wrap up this course with one example or one application of the theory of permutations, and it's related to an episode of Futurama that aired quite a number of years ago. So Futurama, animated television series from creators of The Simpsons. And so that was Matt Groening. And also created by David X. Cohen, whose picture is there. And it's produced by Ken Keeler. And if you look at their credentials, David Cohen has a BA in physics, master's in computing science from Berkeley, and Ken Keeler has a PhD in applied math from Harvard. So they're both involved with Futurama. And there's a quote from David Cohen there that says, "We wanted to get in as much science as possible where it didn't clog up the gears of the story. Our hope is that although such material will fly by most people unnoticed, it might make diehard fans of the people who do appreciate it." If you go back and you watch a lot of the Simpsons and Futurama episodes, you do find that there's a lot of mathematical physics and computing science related content, which is very, very cool to see. What I want to do is I just want to pick one episode in particular, which is related to the material that we've been talking about in this course. That is permutations. And we'll watch the episode. I've trimmed the episode down quite a bit. Usually it's 22 minutes long as an episode. I've trimmed this one down to about 8 minutes, which gets to the heart of the matter, the things that we are interested in terms of permutations. And then we can see what kind of problem arose in the story and how we could potentially solve it. This particular story, Prisoner of Benda, is related to an older story, but rewritten for the Futurama age. Ken Keeler, as you can see, he's got an applied math degree, wanted to prove something new in mathematics and make that new innovation to be the idea that is needed to solve the problem in the episode. So he invented a problem in the episode for which he had actually developed a solution to that problem. And the way he published the result is by a single, fraction of a second screenshot at the end of the episode, where there's a blackboard with a proof on it. And that proof of a subsequent result that's stated in the episode became known as Keeler's theorem. And there's been subsequent work on optimizing Keeler's theorem, etc., regarding permutations. So that's sort of the background of this episode. What I want to do is I just want to show the episode, the trimmed down version of it, and then we can talk a little bit about it at the end. So I'm going to share the video. I'm going to have to stop the recording here because it's copyrighted material and I can't post the lecture on YouTube if I've got this in here. But when we come back from the video, for those who didn't get a chance to see it, I will just explain what the underlying permutation problem was. So I'm just going to pause our recording. Okay, so we're back. Yeah, so that was the episode. Just to summarize what happened in the episode, there was a mind switching machine, and through a flurry of mind switching activities, a whole bunch of minds got swapped to various bodies. And so this is a record of the swaps that took place. So there was switch 1 through switch 7. And that ended up in a resulting permutation of minds to bodies, which I've written down below. So the professor's mind is in Bender's body, the Bender's is in the Emperor's body, the Emperor's in the bucket's in Amy, Amy's in Hermes in Leela's, and then Leela's back in the professor's, and then Fry and Zoidberg's minds have been swapped as well. And then so through a product of 2 cycles, we end up getting some permutation that happened. Now, the key part to the episode was what they referred to as the cerebral immune response. And that is, once two bodies have been in the machine together, those two bodies have built up an immunity to each other, cerebral immunity, and so they can't appear in the machine again together. So for example, since Amy and the professor appeared in the machine in switch number 1, you can't put Amy and the professor in the machine again together. Even if they've got different minds in their heads, it doesn't matter. The physical bodies can't be put in there and have their minds swapped. And so part of the episode then revealed that, hey, wait a minute, this is a problem that we need to solve. How many new bodies do we have to bring into the problem in order to use them as sort of the transient hosts for minds to swap through to get all of the minds restored? And this was Keeler's problem that he ended up solving, and that is that he proved you need at most 2 extra bodies, new bodies, fresh hosts, to come into the mix. And those were the Harlem Globetrotters that appeared in the episode. So, of course, it would be fun if we could figure out if we can solve this ourselves. So what I've done is, give me 1 second. I built an applet and you can play around with it. I'm just going to show the viewer where to find it in the video, and I will post the link in the chat. Actually, I'll post the link in the chat right now so you can get it up and running. So the link is in the chat. For those who are joining by watching the video afterwards, if you go to the lectures page of our course website, at the very bottom of all the lectures, there will be an X for extension or extra lecture, and then you can click on that link and it'll open up the Futurama puzzle. If it's too big for your screen, you can always minimize it like I'm doing now. I'm just minimizing it so it'll fit into my screen. The way the applet works is, this is the configuration of all of the brains and minds that got swapped by the end of the episode. We've got our 2 Globetrotters, who are our fresh bodies, and I've denoted them by X and Y. Those are the only ones we can swap through. So the idea is that we've lost track of who went in the machine with whom, and so there's no point in putting any of 1 through 9 in the machine together, because there's a potential that you won't be able to swap their minds due to the cerebral immune response. So you're going to have to use a Globetrotter every time. The way you can swap them is to use keyboard keystrokes. So if I want to swap X with Bubblegum Tate's mind with the mind that's currently in the professor, then I just hold X and hit 1 at the same time. So I'm holding down X and then I press 1, and that'll swap them. And then you can see the log down below. If I try to swap them again, X1, I get this message that they cannot be swapped due to the cerebral immune response. So I can't reuse that cycle again. So this is your task. You can take the next, 5 minutes or so, or maybe more if you're having so much fun that you just can't stop. Try to see if you can restore all of the minds into their proper bodies with just using these swaps through the Globetrotters. If you get stuck at any stage, or you get this cerebral immune response, or you made a move that you didn't want to move, just refresh the page. I didn't build an undo key into it just because I didn't really have time. This was a last-minute build yesterday. So there's no undo, unfortunately, but there is a page refresh, so you can use that. So feel free to play around with it a little bit. And I'll give you some time here. So I'm just going to mute my mic. And if you have any questions, you can either turn your mic on or post something in the chat. If you are successful, feel free to post in the chat, like got it or some indication. I'll give you about another 2 minutes or so, around 10:55, and we'll come back. All right, everyone. I hope you had a little bit of fun with that. It is a tough one. So if you didn't get it, feel free to keep working on it. Jackie has mentioned in the post that they got it, so I'm gonna stop my screen share, and Jackie, you can share your screen and walk us through your solution. Perfect. I should have asked, do you have a mic? Do you want to turn your mic on, or?
Yeah.
Perfect.
You guys see my
Awesome.
screen?
Yeah, looks good.
All right. So the first thing I thought was I'll swap with Bubblegum Tate's head with Professor Farnsworth. So I did that. And then I noticed, I want to swap with what's on with Bender because Professor's Farnsworth head's on Bender. So I swapped Sweet Clyde's head with Bender. And then I noticed, oh, I can swap Sweet Clyde into Professor Farnsworth now, right? So I did exactly that. And then I continued doing the same thing. I looked at, oh, I see Bender's head is in Professor, let's see, what did I do? No, I swapped with Layla's body with Sweet Clyde, so I could swap. So I'll do the following. Let's see, what did I do? Did Y1, I did now X7, and I swapped into Layla's head, and then I swapped Hermes' head back into his position. And then I did and I swapped Amy's head back in, and then mop buckets back in. I swapped it in accordingly. And now I swapped everything down to here. And all that's left was Fry and Zoidberg, and Bubblegum Tate's and Sweet Clyde's bodies messed up. All right, so the next thing I did was I swapped Fry's with Bubblegum Tate, and I swapped it back with Zoidberg. And then we noticed that we haven't swapped with Bubblegum Tate and Sweet Clyde, so we swapped them now. And then if we swap back with Fry, we will get the solution.
Nicely done. Nicely done. So it looked like you had a bit of a cascading effect that happened at one point, where it was just like, okay, you had a few setup moves, and then all of a sudden you were able to, like dominoes, knock all of the big cycle away. That is awesome. Good job. Thanks for sharing. All right, I'll go back to my screen share. So the idea with the solution to this problem that Ken Keeler came up with is that no matter what the resulting permutation is, in our case, it was a 7-cycle and a 2-cycle, or in the case of the episode, but no matter what the permutation is, you can always restore them with using, at most, as I said, with at most 2 extra players. So I'm just going to indicate or scroll to, actually, before I scroll to that, so this was our switches. These were the steps in the episode, which happened right at the end. I'll try to get them all in there, which was the solution. So the swap backs. And so each picture gives an indication of the swap. So there was I started with the Fry and the Zoidberg and solving that one. So those are the first 4 panels. And then the next panels are all about restoring that other cycle. And so how many swaps here? 2, 4, 6, 8, 10, 12, 13 swaps in total to restore it. And this is the inversion theorem that was stated in the episode. It was known as Sweet-Clyde's inversion theorem. In the episode, that's what it was called. Now in the general populace, it's known as Keeler's theorem, after Ken Keeler, who wrote that episode, or at least the mathematics behind that episode. And so Sweet-Clyde's inversion theorem says, basically, no matter how permuted up your minds are, they can be restored using at most 2 extra players. And if we translate that into our permutation language, it says for any permutation in Sn, so any permutation on n people, there exists 2 cycles in Sn plus 2, so the permutations on n objects plus 2 extra objects, such that the permutation can be restored or can be turned to the identity by multiplying by tau 1, tau 2, all the way up to tau L. In other words, those are the swaps that we need to restore it, with the extra condition that all of the tau i's are distinct. That's the cerebral immune response issue. And all of the tau i's involve at least one of the 2 extra players. So they involve either n plus 1 or n plus 2. And that was due to the fact that there was a frenzy of swapping. So we didn't know who got put in the machine with whom. And so there's no point in even going with 2 original people to put in the machine. Just always use the new players. And then in the episode, they had a screenshot. You probably saw it right at the end, right after they said Sweet-Clyde's inversion theorem. They gave a screenshot of this. And I'm going to zoom in as best I can. And you can see, first let pi be some k cycle on the numbers 1 to n. Without loss of generality, write pi is equal to, and you can see they're using array form now. 1 went to 2, 2 went to 3, k went to 1, k plus 1 went to k plus 1. So all the other ones are the identity. The first k terms have been permuted. And here angle bracket AB represents the 2 cycle. We used round brackets with a space between them, but they're using angle brackets with a comma between them. Represent the transposition that switches the contents of A and B. By hypothesis, pi is generated by distinct switches in n. In other words, pi can be factored as into a product of distinct 2 cycles. And then we introduce 2 new bodies, x and y. So we extend the permutation into its array form, and so on. So there's a full proof written out here, embedded in that episode. And then they write down, here's how you restore the cycle. That's sigma. You first swap x and 1, and then x and 2, and then all the way down to x and I. And then you do y and I plus 1, y and I plus 2, and so on. And so there's a solution to this problem that fixes a single cycle. And then it talks a little bit about what it changes. And then once you've done that individual cycle, what happens is you fix the cycle. I'm just going to grab my pencil, which is hiding. You fix the cycle, but at the cost of perhaps having Bubblegum Tate and Sweet-Clyde being swapped. And then you do the next cycle and the next cycle, however many cycles there are. And each time you end with Bubblegum Tate and Sweet-Clyde having been swapped or not. And so at the very end, either Sweet-Clyde and Bubblegum Tate have been swapped or they haven't been swapped, in which case you can restore them by just using those 2 in the machine themselves. And in this particular case, when we look back at the solution, we see that Sweet-Clyde and Bubblegum Tate never got put in the machine together. And this is a consequence of the fact that there was an even number of disjoint cycles that was the permutation in the end. It was a 7 cycle and a 2 cycle. So anyways, that was known as Keeler's theorem. And the proof is in the episode. So there's a publication. There's a publication of Keeler's theorem, and then that's how it became known as Keeler's theorem. And since then, people have tried to optimize it. In other words, can we do it in less than the number of permutations, the number of swaps that Keeler's theorem indicates? And so I'll indicate what Keeler's theorem actually did. So this is taking that stuff from the blackboard or that green board and writing it out. So Keeler's method for constructing the permutation is you start with a cycle C1 and let x and y be the 2 extra bodies. So what we're going to do is we're going to swap x1 and y and a1, x and ak, and then y and ak, and then do some stuff. Reading it, might be a little bit dense, so let's just do it. And this is pretty much the solution Jackie had as well. So the way I'm going to sort of try to capture this is I'm going to use sweet Clyde, let me get this sort of in the picture. I'm going to use the outermost Globetrotter and the outermost person in the 7 cycle. So this is the professor's body. So I'm going to do a 1Y switch. So I'm going to switch the minds of the bodies on the extremities, the 1 and the Y. So I do a 1 and a Y. And then what I'll do is I'll do the innermost ones. So the X and the 7. So I'm just working on that 7 cycle. So we'll do the X and the 7. And this is pretty much what Jackie ended up doing. He swapped 2. It was Bender that was involved in his, but same idea. Swap 2. So now the Globetrotters are in the mix. And now with that X we only swapped with 7. So I can still do X with the rest. And so now I do this sort of domino effect where X gets swapped with 6 to restore Hermes, then 5 to restore Amy, then 4 to restore the Mop Bucket, then 3 to restore the Emperor, and 2 to restore Bender, and 1 to restore the Professor. So I kind of use Bubblegum Tate, or X, as this sort of revolving door that all the minds just started filtering through. And then Leela still has to go home. That's Y and 7, and we haven't done a Y7, as we can see from our mapping log. So we do a Y7. So that restored that cycle, but the Globetrotters have now had their minds swapped. So at first glance, someone might look at this and go, oh, okay, let's swap their minds. But no, we don't need to, because we can do their mind swap at the end if necessary. So now we do the same thing with the 2 cycle. We can do the outermost ones. So that would be 8 and Y. So I'll do an 8Y. And the inner ones, which is the 9X. And then now I've removed the minds from the 2 bodies I'm trying to fix. They're out in the Globetrotters. And now I can restore them by doing the opposite. Instead of the 8Y, I now use the 8X. And instead of the 9Y, the 9X, I now use the 9Y. And that solved them. And it restored the 2 Globetrotters. If there was another cycle, I would just attack that next cycle and the next cycle and the next cycle. So that's the idea with Keeler's theorem, is we go ahead and we first get the minds out of the first and the last body and switch them with the Globetrotters. There was this move here that Keeler had done at this point, but it doesn't have to be done there. It could be done at the end. It's disjoint from all the other 2 cycles. So then we did this sort of domino effect where everyone just got cycled through to replace them all. And then that last 2 cycle, YAK, can fix the rest. And so that sigma 1 basically did the inverse of the 7 cycle at the cost of mixing up the Globetrotters. And then we could do it again. And so this was Keeler's theorem sort of laid out in its general form. The improved version, which made its way into the literature, is that you can, so Keeler's theorem, if you count them all up, it's going to either take n plus 2r plus 1 2 cycles, or n plus 2r 2 cycles, depending on whether r is even or odd. In other words, depending on whether I have to switch the Globetrotters at the very end or not. In this case, we had r cycles. There was 2 cycles. There was a 7 cycle and a transposition. So there's only 2 cycles to restore. So r is 2. N was 9 because there was 9 people. So it was a case where r is even, and we needed 13. So it was a 9 plus 4 or 13 2 cycles to fix it. The literature came up with a improved version, which only needs n plus r plus 2 disjoint transpositions to solve. It turns out that this is 13 in this case as well, because n plus 2 plus 2, or 9 plus 4 is 13. So this improved version still gives us 13 in the case of what happened in the episode, but for more general permutations, it's the optimized version. And so there's a paper that came out with this optimized form in it as well, which was kind of fun to see. What I'll do is I will post these, now that we've sort of seen this, I'll post the filled in version of these notes just so you have them. I didn't want to do it beforehand because I wanted to focus more on the play aspect rather than the individual details. But that's it. So there was an example of mathematics making its way into pop culture and a proof being published in a funny and sort of whimsical way. Anyways, that's it for today. Hope you enjoyed it. I am going to stop the recording and then we can just have a chat. All right. Oh, and that's it for the course too, I guess. So, good luck with the presentations next week.